Welcome to Bethlahem Institute of Engineering. Bethlahem Institute of Engineering is affiliated to Anna University, Chennai and approved by AICTE, New Delhi. This institution was established in the year 2008.
Okay, last class some fundamentals engineering thermodynamics. The class some phases and some fundamentals of thermodynamics last class but what is the unit of thermodynamics and concept of இதெல்லாம் வந்து லாஸ்ட் கிளாஸ்ல பார்த்தோம். கான்செப்ட்ல பார்த்தீங்கன்னா லாஸ்ட் கிளாஸ் 10ல பார்த்தோம். லாஸ்ட் we'll already discussed the introduction of kinematics of theory of gases, definition of thermodynamic system, what is the system and boundary and surroundings, closed system, open system, isolated system, adiabatic system and homogenic system, heterogenic system, what is meant by macroscopic and macroscopic point of view, pure substances, thermodynamic equilibrium. So properties of system, state, இதெல்லாம் வந்து லாஸ்ட் கிளாஸ்ல பார்த்தோம். The fundamentals of thermodynamics. So in the class process also it was already discussed in the last class. Processes, cycles, point function, path function, temperatures, and these fundamentals also already I was explained in the last previous classes. And Isothermal of thermodynamics and thermodynamic and scale of property, measurement of temperatures. These are also I was already explained in the last classes. Specific volume, what is meant by specific volume, and reversible and irreversible process, energy, work and heat. So work and heat, these also already I was explained in the last classes. Today I will explain some of fundamental problems also. And in the last classes, what is mean by first law of thermodynamics and internal energy, law of conservation of energy, first law of thermodynamics, application of first law of process, energy, and property of the system, what is mean by perpetual motion machines, and first kind of TMM1. These also already I was explaining in the last classes. Energy and isolated system, these also already explained in the last classes. Today I will explain some fundamental problems in the first unit. Okay. Some fundamental problems in the first units. Just a minute, wait, I will explain. First, we go to the fundamentals of problems, then we go to the main problems. In the first unit, all the problems are simple. First, we will explain the summary of perfect gases. So, in the summary of perfect gas equations, I was already explained in the last classes, but today also I will explain some fundamentals, some fundamental formulas also I will explain. Okay, just a minute, I will explain. Okay, the application of the 1 minute. What is meant by enthalpy? One of the fundamental quantities which occur irreversibly, invariably in thermodynamics is the sum of the internal energy U and pressure volume product PV. The sum is called enthalpy. So, IT is equal to internal energy is equal to U plus PV. So, U plus PV, U is means internal energy and PV is equal to pressure and volume deviations. So, another the enthalpy of the fluid in the is the property of the fluid since it consists of the sum of the property and product of two properties. So generally, what is we have considered the enthalpy of the fluid, since the consist of the fluid is sum of the property of the product of two properties. Two properties we have to analyze. Only is internal energy, another is pressure and volume. These pressure and volume would be these deviations or these adding you should be analyzed in the enthalpy. Since enthalpy is a property like internal energy, pressure, specific volume, and temperature. And internal energy is considered with the internal energy, pressure, specific volume, and temperature. It can be introduced into any problem. It can be introduced into any problem, whether the process is flow or non-process, non-flow process. So already I was explaining what is mean by flow process and what is non-flow process. The total enthalpy of mass m of the fluid can be H is equal to U plus internal energy U plus PV, where H is equal to mass into internal energy is equal to the mass m into H. So the perfect of the equation H is equal to U plus PV. Perfect equation H is equal to U plus PV. So constant volume at the temperature plus gas constant is R into T. PV is equal to R into T in gas constant. So in CV, so we have to apply into CV plus R into the commonly we can take into the T in the outside. So CP is equal to generally CP is equal to PV is equal to RT. CP by CV is equal to R. CP by CV is equal to R. So this relation is used to this equation. Then CP into T. Then H is equal to CPT into T. And capital H is equal to MCP into mass into CP. Um, constant pressure and into temperatures. Note that since so U is equal to internal energy U is equal to 0, temperature is equal to 0, then H is equal to 0 and the T is also is equal to 0. The ratio of specific heats, at a constant pressure to specific heat at a constant volume is given the symbol gamma. I'll explain the ratio of specific heats. The ratio of specific heat at a constant pressure to specific heat at a constant volume is given the symbol gamma. So general the ratio of specific heat, ratio of specific heat at constant pressure process, and ratio of specific heat at constant pressure, specific heat at constant volume is which is a ratio. ரெண்டுக்கும் உள்ள ratio என்ன சொல்லுவோம்? Specific heat at a constant pressure and specific heat at a constant volume symbol gamma சொல்லுவோம். Where gamma is equal to Cp by Cv. Since Cp is equal to gamma என்ன சொல்லுவோம்? Gamma is equal to Cp by Cv. எப்படி சொல்லுவோம்? Cp by Cv is equal to R. ஸோ அதுல இருந்து இந்த ஃபார்முலா நம்ம எடுத்துருக்கோம், ட்ரை பண்ணிருக்கோம். Where Cp is equal to Cp எழுதுனா அப்ப என்ன ஒன்று பண்ணலாம்? Cp is equal to Cv into Cv plus R. So Cp is equal to என்னது? Cv plus R சொல்லுவோம். Plus R. It is clear that Cp must be greater than Cv. So constant pressure எப்படி இருக்கும்? Greater than constant volume for any perfect gas. ஸோ ஏதாவது என்னன்னா பர்ஃபெக்ட் கேஸ்னா லட்சிய வாயு அப்படின்னு தமிழ்ல சொல்லுவாங்க. பர்ஃபெக்ட் கேஸ் மீன்ஸ் எல்லா பர்ஃபெக்ட் கேஸ்லயும் என்ன இருக்கும்? சிபி இஸ் மஸ்ட் கிரேட்டர் தேன் சிவியோட என்னது சிபி வந்து கூடுதலா இருக்கும். இட் ஃபாலோஸ் தேர் ஓர் தட் த ரேஷியோ சிபி பை சிவி இஸ் ஈக்குவல் டு காமா இஸ் ஆல்வேஸ் கிரேட்டர் தேன் யூனிட்டி. ஸோ சிபி பை சிவி காமா எப்பவுமே வந்து என்னது இருக்கும்? கிரேட்டர் தேன் யூனிட்டினா ஒன்னை விடவும் கூடுதலா இருக்கும். இன் ஜெனரல் அப்ராக்சிமேட் வேல்யூஸ் ஆஃப் காமா ஆர் ஃபாலோஸ் ஃபார் monoatomic gases such as argon, helium எப்படி இருக்கும்னா is equal to 1.6 இருக்கும். The diatomic gases such as carbon monoxide, hydrogen, nitrogen and oxygen எப்படி இருக்கும்? 1.4 இருக்கும். So Cp by C is equal to gamma. It's always greater than unity. So ஒன்னோட அதிகமா இருக்கும். In general, approximate value of gamma is are as follows. For monoatomic gases such as argon, helium அதுக்கு எவ்வளவு இருக்கும்? 1.6. For diatomic gases such as carbon monoxide, hydrogen, nitrogen, and oxygen is equal to 1.4. For triatomic gases such as carbon dioxide and sulfur dioxide is equal to 1.3. So triatomic gases such as carbon dioxide and sulfur dioxide is equal to 1.3. For some hydrocarbons, the value of gamma is equal to quite low. So hydrocarbons எடுத்துக்கிட்டேன்னா gamma வந்து என்னது கொஞ்சம் குறைவா இருக்கும். Example, for ethane gamma is equal to 1.22. For isobutane gamma is equal to, so பார்த்தீங்கன்னா ஈத்தேனுக்கு எப்படி எடுத்துக்கலாம்? 1.22 எடுத்துக்கலாம். For isobutane gamma is equal to 1.11. So application of first law of thermodynamics. So application of first law of thermodynamics to non-flow or closed system. So first பார்த்தீங்கன்னா first இந்த fundamental application of first law of thermodynamics. thermodynamicsல non-flow process, flow process. நான் last classல I was already explained. Or closed systemல reversible constant volume or isothermal process. ஸோ நம்ம ஏற்கனவே பார்த்தோம் ஐசோபாரிக் ஐசோபாரிக் இதெல்லாம் வந்து கிளாஸ்ல ஆல்ரெடி எக்ஸ்பிளைன் பண்ணிட்டோம். இருந்தாலும் திரும்ப ஒருக்க அதை வந்து என்ன பண்ணும், அதை வந்து நீட்டா வந்து ஒரு கூட எக்ஸ்பிளைன் பண்ணும். ஸோ ரிவர்சிபிள் கான்ஸ்டன்ட் வால்யூம் இஸ் ஈக்குவல் டு ஐசோசாரிக் ப்ராசஸ் வால்யூம் இஸ் ஈக்குவல் டு கான்ஸ்டன்ட். எப்பவுமே வந்து என்னது, வால்யூம் வந்து கான்ஸ்டன்டா இருக்கும். ஸோ அதான் வந்து பிவி இஸ் ஈக்குவல் டு வால்யூம் கான்ஸ்டன்ட் வால்யூம் ப்ராசஸ் சொல்லலாம். இதுக்கு இன் ஏ கான்ஸ்டன்ட் வால்யூம் ப்ராசஸ் த ஒர்க்கிங் சப்ஸ்டன்ஸ் இஸ் கன்சிடர்ட் இன் ஏ ரிஜிட் வெசல். ஸோ ஒரு க்ளோஸ்ட் வெசல்ல என்ன பண்ணும், கான்ஸ்டன்ட் வால்யூம் ப்ராசஸ் ஒர்க்கிங். ஸோ நம்ம என்ன சப்ஸ்டன்ஸை ஒர்க் பண்ணோமோ அதை வந்து க்ளோஸ் வெசல் வச்சிருக்கோம். அகேன்ஸ்ட் த பவுண்டரிஸ் ஆர் ஆஃப் த சிஸ்டம் immovable and no work can be done on or by the system. So against the boundaries are of the systems are immovable. So நான் ஏற்கனவே சொன்னேன். ஸோ அந்த சிஸ்டத்துக்கு அவுட் சைடு இருக்கக்கூடிய அந்த லேயர் வந்து பவுண்டரி இஸ் ஏ இமேஜினரி ஒன். ஸோ நம்ம பவுண்டரி இந்த கான்ஸ்டன்ட் வால்யூத்தில் பவுண்டரி மூவ் ஆகுது. பவுண்டரிஸ் ஆர் இன் ஃபிக்ஸட், the system are immovable and no work can be done on or by the system. So அந்த ஒர்க் வந்து என்ன செய்யாது, நோ ஒர்க் கேன் டன், ஒர்க் அதனால நடக்காதான், ஆர் பை த சிஸ்டம், இந்த சிஸ்டம்ல நடக்காது, அதர் தேன் பேடல் வீல் ஒர்க் இன்புட்ஸ். ஸோ அதர் தான் என்னது, எக்ஸாம்பிள் என்னது, பேடல் வீல். ஸோ லாஸ்ட் கிளாஸ்ல பேடல் வீல் எக்ஸ்பெரிமெண்ட், ஜூல்ஸ் எக்ஸ்பெரிமெண்ட்டை பற்றி எக்ஸ்பிளைன் பண்ண லாஸ்ட் கிளாஸ்ல. இட் வில் பி அசியூம்ட் தட் கான்ஸ்டன்ட் வால்யூம் இம்ப்ளைஸ் ஜீரோ ஒர்க். ஸோ இது வந்து என்னது, கான்ஸ்டன்ட் வால்யூம் ஒர்க் வந்து ஜீரோ ஒர்க் அன்லெஸ் ஸ்டேட்டட் அதர்வைஸ். ஸோ அதை அதர்வைஸ் என்ன செய்யலாம், அன்லைஸ் ஸ்டேட் தட் நோ ஒர்க் நடக்காது, வால்யூம் வந்து கான்ஸ்டன்டா இருக்கும். ஃபார் பார்த்தீங்கன்னா ஃபிகர் ஷோஸ் என்ன இருக்கு, ஒரு கேஸஸ் உள்ள கேஸ் இருக்கு, மேல பிக்சடா இருக்கு. ஸோ இந்த ரெண்டு எண்ட்லயும் பாத்தீங்கன்னா இந்த எண்ட் டூ எண்ட்ஸஸ் ஆர் என்னது லாக், ரெண்டு எண்டையும் லாக் பண்ணி வச்சிருக்காங்க. ஸோ வந்து கேஸை எவ்வளவுதான் நீ ஹீட் பண்ணாலும் தேர் இஸ் நோ சேஞ்ச், பிகாஸ் இந்த கேஸ் உள்ளதான் எக்ஸ்பேண்ட் ஆகும், வால்யூம் இஸ் இன் கான்ஸ்டன்ட். ஸோ வால்யூம் கான்ஸ்டன்டா இருக்கு, ஏன்னா அந்த எண்ட்ல இருக்கக்கூடிய பிஸ்டன் மூவ்மெண்ட் இருக்காது. பிஸ்டன் இஸ் என்னது, பிஸ்டன்ல உள்ள ரெண்டு எண்டம் என்ன பிக்சடா இருக்கு. ஸோ ரெண்டு டாப்பர் வச்சிருக்காங்க. ஸோ வந்து என்ன செய்யும், வால்யூம் இஸ் கான்ஸ்டன்ட். ஹியர் த ஃபிகர் ஷோஸ் பிவி டயக்ராம் பார்த்தீங்கன்னா V1 இஸ் ஈக்குவல் டு V2. V1ல என்ன இருக்கோ வால்யூம் இருக்கோ V2. ஸோ கான்ஸ்டன்ட் வால்யூம் ப்ராசஸ். செகண்ட், அதை எப்படி எழுதலாம், கன்சியூமிங் மாஸ் ஆஃப் ஒர்க்கிங் ஸ்டப்ஸ் யூனிட்டி ஒன்றுன்னு இருந்தா அண்ட் அப்ளைங் ஃபர்ஸ்ட் லா ஆஃப் தெர்மோடைனமிக்ஸ் ப்ராசஸ். நம்ம பார்த்தோம் ஏற்கனவே, ஃபர்ஸ்ட் லா பார்த்தோம், ஃபர்ஸ்ட் எக்ஸ்பிளைன். ஃபர்ஸ்ட் லா சீக்கல் டு Q, heat transfer equal to U1 internal energy, final internal energy minus final internal energy minus என்னது first internal energy U1 U2 minus U1 into plus work done. ஸோ இங்க பார்த்தீங்கன்னா the work done is equal to W. ஸோ integral work done is equal to 1 to 2 எடுத்துட்டா first process, 1ல இருந்து second process, P in terms of pressure, in terms of என்னது volume, pressure in terms of volume. அதனால தான் P into in terms of PdV ன்னு போட்டிருக்கோம். PdV is equal to 0. பிடினா என்னது, நம்ம வந்து ப்ரெஷர் அதில் இன்க்ரீஸ் ஆனோம், ஆனால் வந்து வால்யூம் வந்து நோ சேஞ்ச். ஸோ வால்யூத்தில் சேஞ்ச் ஆகுது. ஸோ அதனால பிடிவி சிக்கல் டு 0 ஆஸ் த டிவி சிக்கல் டு 0. அதனால என்னது, டிஃபரன்சியேஷன் டிவியை இன்டகிரேட் பண்ணேன்னா என்ன வரும், டிவி வந்து 0 இருக்கனால டிவி சிக்கல் டு 0 எழுதுறோம். கியூ சிக்கல் டு ஃபைனல் இன்டர்னல் எனர்ஜி மைனஸ் ஃபர்ஸ்ட் இன்டர்னல் எனர்ஜி சீக்கல் டு U1 மைனஸ் U2 மைனஸ் U1 சீக்கல் டு சிவியை காமன் அழுத்தா சிவி, கியூ சீக்கல் டு சிவி இன் கான்ஸ்டன்ட் வால்யூம் T2 final temperature minus initial temperature. So on the constant volume process பார்த்தீங்கன்னா final temperature minus initial temperature. CV is equal to specific heat at a constant volume. CV னா என்ன எடுத்துக்கலாம்னா specific heat at a constant volume CV is equal to, for mass M is equal to M of working substance. So internal energy U2 minus U1 heat நம்ம அதில் சப்ளை பண்ணுவோம், அந்த இதில் ஒர்க்குக்கு சப்ளை பண்ணும்போது என்ன நடக்கும், இன்டர்னல் எனர்ஜி இன்க்ரீஸ் ஆகும். ஸோ அதனால ஃபர்ஸ்ட் இருக்கக்கூடிய இன்டர்னல் எனர்ஜியோட செகண்ட் வந்து இன்டர்னல் எனர்ஜி இன்க்ரீஸ் ஆகும். ஸோ இன்டர்னல் எனர்ஜி U2 மைனஸ் U1 சீக்கல் டு மாஸ் இன்டு கான்ஸ்டன்ட் வால்யூம் இன்டு டெம்பரேச்சர், ஃபைனல் டெம்பரேச்சர் மைனஸ் இனிஷியல் டெம்பரேச்சர். ஸோ ஜெனரலி மாஸ் இன்டு வால்யூம், மாஸ் இன்டு இன்டர்னல் எனர்ஜி M is equal to capital U. ஸோ மாஸ் இன்டு இன்டர்னல் எனர்ஜி ஸ்மால் எனர்ஜி என்தால்பி சீக்கல் டு அதை எப்படி எழுதலாம், சீக்கல் டு யூன்னு எழுதலாம். ஸோ ரிவர்சிபிள் கான்ஸ்டன்ட் ப்ராசஸ் ஆர் ஃபர்ஸ்ட் நம்ம பார்த்தது கான்ஸ்டன்ட் வால்யூம் ப்ராசஸ். செகண்ட் என்ன பார்க்க போறோம், ரிவர்சிபிள் கான்ஸ்டன்ட் ப்ரெஷர் ப்ராசஸ், அதர்வைஸ் ஐசோபாரிக் ப்ராசஸ். ஸோ இங்க வந்து பார்த்தீங்கன்னா B is equal to constant. In isobaric process P is equal to, P means pressure is equal to constant. So last பார்த்தது volume is equal to constant. So it can be seen that in the figure when the boundary of the system is inflexible. So as in a constant volume process. So the boundary of the system என்னது flexible இருக்காது, inflexible இருக்கும். So reversible process என்ன pressure constant inflexible. As in a constant volume process, then the pressure rises when heat is applied. Pressure rise ஆகும், heat supply பண்ணும்போது, hence for a constant pressure process, the boundary must move against an external resistance as heat is applied for instance of gas. In a cylinder behind a piston can be made to undergo a constant pressure process since the piston is pushed through a certain distance by the force exerted by the gas, then the work is done by the gas on the surroundings. So what is happen? So first என்ன நடக்கும்னு பார்த்தீங்கன்னா நான் வந்து piston and cylinder arrangement gas வந்து நம்ம ஹீட் பண்ணுவோம். Gas is initially heating the gas. The piston is moving, initial piston moving, initial stage ல இருந்து final stage வரைக்கும் என்ன செய்யும் மூவ் ஆகும். ஸோ இப்போ நடக்கும் இந்த ப்ராசஸ் ஃபர்ஸ்ட் பார்த்தீங்கன்னா கான்ஸ்டன்ட் வால்யூம் பட் த ப்ரெஷர் இஸ் கான்ஸ்டன்ட். ப்ரெஷர் வந்து இங்கே கான்ஸ்டன்டா இருக்கும். வால்யூம் வந்து என்னது சேஞ்ச் ஆகும். வால்யூம் வந்து இனிஷியல் வால்யூம்ல இருந்து V1ல இருந்து V2 கன்வெர்ட் ஆகும். ஏன்னா ப்ரெஷர் இன்க்ரீஸ் ஆகும்போது இங்க வந்து நோ ஸ்டாப்பர் அரேஞ்ச்மெண்ட் இஸ் நீடட். இங்க வந்து ஸ்டாப்பர் அரேஞ்ச்மெண்ட் எதுவுமே கிடையாது. ஸ்டாப்பர் எதுவுமே கிடையாது. டைரக்டாவே என்ன பண்ணும் நம்ம வந்து ஹீட் பண்ணும்போது அந்த பிஸ்டன் வந்து ஃபர்ஸ்ட் ஸ்டேஜ்ல இருந்து செகண்ட் ஸ்டேஜுக்கு மூவ் ஆகும். ஸோ இதனால என்ன செய்யும் ப்ரெஷர் வந்து ரைஸ் ஆகும். ஸோ ரைஸ் ஆகி ஒரு சேட்டன் எக்ஸ்டென்ட் மேலே என்ன செய்யாது ப்ரெஷர் ரைஸ் ஆகாது. ஆனா வந்து எனக்கு ப்ரெஷர் வந்து கான்ஸ்டன்டா இருக்கும் அது வரைக்கும். ஸோ ஆனா என்ன நடக்கும் ப்ரெஷர் கான்ஸ்டன்டா இருக்கும். ஆனா நம்ம ஹீட் பண்ணனால ஒர்க் நடக்கும். ஸோ அதான் சொல்லியிருக்கான். இட் ஹேட் சீன் தட் த பவுண்டரி ஆஃப் த சிஸ்டம் இஸ் இன்ஃபிளெக்சிபிள். ஃபிளெக்சிபிள் இல்லை என்னது ஃபிளெக்சிபிளா இல்லை இன்ஃபிளெக்சிபிளா இருக்கும். சரியா? as it is as in a constant volume process inflexible இருக்கும். Then the pressure rises in the heat is applied. Hence for a constant pressure process இங்க பார்த்தீங்கன்னா pressure வந்து என்ன செய்யும் இன்க்ரீஸ் ஆகும். The boundary must go against an external resistance. Boundary என்ன செய்யும் external resistance மேல என்ன செய்யும் must go as heat is applied. For instance, in a cylinder behind the piston can be undergo a constant pressure process since the piston pushed through a certain distance. ஒரு distance வரைக்கும் போகும். அதுக்கப்புறம் என்ன செய்யும் வால்யூம் வந்து கான்ஸ்டன்டா இருக்கும். ஸோ அதான் சொல்லியிருக்கான். The PV diagram indicates PV diagram என்ன indicates பண்ணுது? PV diagram indicates that PV diagram indicates the source, the system of state source, the system and states before and after the heat addition of the constant pressure. First பார்த்தீங்கன்னா என்னது V2 வால்யூம். இந்த வால்யூம் வந்து என்னது அப்படி V1 V2 வந்து இதா இருக்கு. இனிஷியலா பார்த்தீங்கன்னா வால்யூம் சுமாலா இருக்கு. இனிஷியல் வால்யூம் இஸ் சுமால் எக்ஸ்டென்ட். அடுத்த பார்த்தீங்கன்னா என்னது ஃபைனலா வந்து டோட்டலா என்ன செய்யுது V1ல இருந்து V2க்கு என்ன செய்யுது வால்யூம் வந்து சேஞ்ச் ஆகுது. ஸோ அதனால V2 மைனஸ் இந்த V1 எப்படி ஃபைண்ட் அவுட் பண்ண முடியும் V2ல இருந்து V1 மைனஸ் பண்ணும். அதனால ஃபைனல் வால்யூம் மைனஸ் இனிஷியல் வால்யூம் P is equal to in terms of pressure change ஆயிருக்கு. P is equal to V2 final volume minus initial volume. So in constant pressure process பார்த்தீங்கன்னா என்ன நடக்குது P is equal to V2 final volume minus initial volume. So constant pressure வந்து கான்ஸ்டன்டா இருக்கு. ஸோ certain extentல pressure கான்ஸ்டன்டா இருக்கு. ஸோ ஆனா பார்த்தீங்கன்னா pressure கான்ஸ்டன்டா இருக்கு. வால்யூம் வந்து என்ன செய்யுது சேஞ்ச் ஆகுது. ஓகே வால்யூம் வந்து என்ன செய்யுது சேஞ்ச் ஆகுது. V1ல இருந்து V2க்கு மாறிடுது. ஸோ அதான் எப்ப என்ன எழுதலாம் கன்சிடரிங் யூனிட் மாஸ் ஒர்க்கிங் substance applying the first law of thermodynamics எல்லாமே first law of thermodynamics formula Q is equal to U2 minus U1 plus W work done. So internal energy final internal energy minus internal energy so plus என்னது work done எவ்வளவு நடந்தது work done is equal to W is equal to integral 1 to 2 P into dV. So இதான் general formula in terms of என்னது pressure in terms of என்னது வால்யூம் சேஞ்ச் இன் வால்யூம். ஸோ அதனால P இன்டு இன் டேர்ம்ஸ் ஆஃப் என்னது டிவி. ஸோ P இஸ் ஈக்குவல் டு நம்ம என்ன எழுதும் P இன்டு வால்யூம் சேஞ்ச் ஆயிருக்கு. ஸோ அதனால V2 மைனஸ் ஃபைனல் வால்யூம் மைனஸ் இனிஷியல் வால்யூம். ஸோ இதை இக்குவேஷன் 1ல நீ அப்ளை பண்ணா Q இஸ் ஈக்குவல் டு U2 மைனஸ் U1 பிளஸ் ஸோ நம்ம ஏற்கனவே நம்ம என்ன அப்ளை பண்ணியிருக்கோம் இன்டர்னல் எனர்ஜி ஃபைனல் இன்டர்னல் எனர்ஜிலேருந்து ஃபர்ஸ்ட் இன்டர்னல் எனர்ஜி என்ன பண்ணும் இன்டர்னல் எனர்ஜி ஃபர்ஸ்ட் இருந்தால் மைனஸ் பண்ணும். ஸோ அதனால U2 மைனஸ் U1 பிளஸ் அதோட ஒர்க் டன் என்ன நடந்திருக்கு ஒர்க் டன் எப்படி நடந்திருக்கு வால்யூம் வந்து சேஞ்ச் ஆயிருக்கு. ஒர்க் டன் வந்து நம்ம கேஸ்ல வந்து ஹீட் பண்ணனால வால்யூம் சேஞ்ச் ஆயிருக்கு. ஸோ அதனால P இஸ் ஈக்குவல் டு சாரி P இன்டு V2 மைனஸ் V1 ஃபைனல் வால்யூம் இனிஷியல் வால்யூம் ஃபைனல் வால்யூம் மைனஸ் இனிஷியல் வால்யூம் ஈக்குவல் டு U2 minus U1 into Q is equal to U2 minus U1 plus P V2 minus V1. ஸோ அதை வந்து என்ன பண்ணலாம் உள்ள வந்து மல்டிப்ளை பண்ணேன்னா P into V2 minus minus PV1 அப்படின்னு ஒரு ஈக்குவேஷன் Q is equal to ஸோ எகைன் வந்து H is equal to U plus V ஃபார்முலா உனக்கு தெரியும் H is equal to enthalpy U is equal to U internal energy plus pressure into volume change pressure into volume. ஸோ அதில் அப்ளை பண்ணலாம் H is equal to அந்த H உள்ள இடத்துல அப்ளை பண்ணலாம். அப்ளை பண்ணால் என்ன வரும் U2 plus PV2 மைனஸ் U1 மைனஸ் U1 plus PV1. ஸோ அதுலேருந்து என்ன பண்ணலாம் H2 மைனஸ் H1 எழுதலாம். Q is equal to எகைன் Q is equal to நம்ம எப்படி எழுதலாம் H2 மைனஸ் H1. ஸோ அதுல என்ன நம்ம என்ன எழுதணும் ப்ரெஷர் வந்து கான்ஸ்டன்டா இருக்கனால H1 is equal to நம்ம ஃபார்முலா H2 minus H1 CP pressure is equal to constant. அதனால constant pressure Cp into T2 minus T1. So H is equal to small h என்னது enthalpy or specific enthalpy ன்னு சொல்லலாம் small h. Cp is equal to specific heat at a constant pressure. Cv is equal to specific volume at a constant specific Cv is equal to constant volume. Cp is equal to specific heat at a constant pressure. Specific heat at a constant pressure. For masses எடுத்துக்கிட்டா for mass எடுத்துக்கிட்டேன்னா m of working substance mh is equal to m into h capital H ன்னு எழுதலாம். So Q is equal to H2 minus so mh is equal to mass into H is equal to என்ன enthalpy. So enthalpy. So அந்த இது எப்படி எழுதலாம் capital H H2 enthalpy minus H1 is equal to mcp into T2 minus T1. So first நம்ம பார்த்தோம் first I was already explained the iso constant pressure process and the constant volume process. இங்க பார்த்தா another one is another isothermal process or reversible temperature process சொல்லலாம். Isothermal process third one is so இங்க வந்து PV is equal to pressure and volume constant, temperature also constant. So temperature, pressure, volume constant, temperature also constant. இது வந்து reversible temperature or isothermal process. A process at constant temperature, a process at constant temperature is called an isothermal process. ப்ராசஸ் வந்து கான்ஸ்டன்ட் டெம்பரேச்சரா இருக்கிறது தான் என்ன பண்ணுவோம் ஐசோதெர்மல் ப்ராசஸ் சொல்லுவோம். when a working substance in a cylinder behind a piston when a working substance ஒரு ஒர்க் பண்ணக்கூடிய சப்ஸ்டன்ஸ் in a cylinder ஒரு சிலிண்டர்ல behind a piston expands from a high pressure piston expands from high pressure to a low pressure, there is a tendency for the temperature to fall. In an isothermal expansion, heat must be added continuously in order to keep the temperature at the initial value. Similarly, in an isothermal compression, heat must be removed from the working substance continuously during the process. So simple, in isothermal process, there is no heat change. So ordinary, the heat exchangers and so many the refrigeration devices, we have used this type of process in isothermal process. The insulation or insulation tab is used to very used to the heat changes. So in isothermal process, there is no heat change. A process at constant temperature is called isothermal process. When a working substance is cylinder and piston arrangements, the low pressure, we have to apply the heat. We have to apply the heat source or any heat. The temperature is changes. The pressure is changes. The pressure is changes. The pressure is pressure and the pressure is low pressure. There is a tendency to temperature is fall. Piston expands from high pressure to low pressure. Piston expands from high pressure to low pressure, and the temperature is to fall. An isothermal expansion, heat must be added. So in isothermal expansions, heat must be added. Heat must means any heating source or heating device is used to heat this heat must be is this process. For example, heat must be added continuously in order to the temperature is keeping constant. So similarly, the isothermal expansion heat must be removed from the working substance. For example, refrigerator, the working substance continuously during the process. So the system is states that before and after heat adding the constant temperature in constant temperature process. Here the figure shows the heat source or any heating device in the inside the piston cylinder arrangement. Inside gas is there and the piston is in the topmost position. So reversible isothermal process, the PV diagram shows the volume is V12, volume is equal to P1, pressure is equal to P1 to P2 to P1. Pressure is equal to P1 to P2 drops and pressure is equal to constant temperature pressure. Pressure is PV is equal to pressure and volumes are in constant. Sorry, pressure and volumes are constant. The pressures and volumes are constant and temperatures are pressure and volume PV is equal to constant. Constant temperature pressure and volume is constant and there is no heat change. There is no heat change in this process. In isothermal process, there is no heat change. In isothermal expansion, there is no heat change. And the considering the unit mass of working substance and applying the first law of process, Q is equal to U2 minus U1 plus W. The general equation is Q is equal to U2 minus U1 plus W. In constant volume process, CB, constant volume process, because here also in constant pressure and volumes are constant. So, CB is equal to temperature, T2 is equal to T1. because there is no heat change, there is no temperature change. So that's initial temperature, final temperature is equal to initial temperature. So that T2 is equal to T1 in constant volume Cv into T2 minus T1 plus work done. In Cv is equal to volume is constant, so 0 plus work done. So integral the work done W is equal to 1 to 2 P into pressure into in terms of dV. So in case of PV is equal to pressure and volume constant, P is equal to C, capital C divided by V, because P is equal to C is equal to constant. Integral work done is equal to V1 volume 1 to 2 volume 1 to 2 C into constant into dV by V, change in volume divided by original volume dV by V plus constant. So change in volume in terms of integral quota 1 by V is equal to general formula. Any any formula we have use 1 by x means log s. Here also same formula is used. 1 by dv by pv is equal to log e power log e v. So integral v2 by v1 is equal to, we have to apply c into log e into v2 by v1. This is the formula where the constant c can be either written as pressure volume p1 v1 or p2 v2. P1 v1 is equal to p2 v2 is equal to constant. In isothermal process, P1 V1 is equal to pressure at initial temperature, pressure volume at initial is equal to pressure volume at final also same. So that constant. So that P1 V1 is equal to P2 V2. Since P1 V1 is equal to P2 V2 is equal to constant. Work done W is equal to P1 V1 log V2 by V1. Formula log V2 by P1 V1 is equal to log constant C is equal to work done log E is equal to V2 by V1 per unit mass of working substance. Per unit mass of working substance. W is equal to P2 V2 log E into V2 by V1 per unit mass of working substance. Q is equal to work done. W is equal to Q heat transfer Q is equal to W is equal to work done is equal to P1 V1 log E into V2 by V1. For mass we have to consider the mass of the working substance P1 V1 log E into V2 by V1. P1 V1 log E power P2 V2 by V1 is equal to P2 by P1. In temperature, because constant volume and constant temperature in this process, so that P2 by V1 is equal to final volume divided by initial volume is equal to P1 initial pressure divided by final pressure. The ratio of final volume to initial volume is equal to the ratio of initial pressure into the final pressure. This is the reversible isothermal process formula. This is an isothermal process. Another one is a reversible adiabatic process. In adiabatic process, reversible adiabatic process, BV power gamma is equal to constant. The formula says BV power gamma is equal to constant. An adiabatic process is one in which no heat is transferred to or form the fluid during the process. Such a process can be reversible or reversible. In one an adiabatic process in which no heat is transferred. There is no heat transfer. In isothermal process, there is the temperature is not changed. So the difference between adiabatic process and isothermal process means in isothermal process the temperature is not changed. The temperature is constant. But in adiabatic process, there is no heat transfer in the outside of the system. There is no heat transfer. So in adiabatic process is one in which no heat transfer to or from the fluid during the process. Heat transfer to or from the fluid during the process. Such a process can be reversible or reversible. So this process is called reversible or reversible. The reversible adiabatic non-flow process will be considered in the system. So in reversible adiabatic process, there is no heat transfer. So non-flow process will be considered in the system. So considering the unit mass of working substance, applying first law Q is equal to U2 minus U1 plus W. So Q, there is no heat transfer. So Q is equal to 0. Is equal to U2 minus U1 plus W. Work done is equal to W. Work done is equal to U2 minus U1 for any adiabatic process. For any adiabatic process, work done is equal to U1 minus U2. Is true for an adiabatic process whether the process is reversible or not. In an adiabatic expansion, the work done W by the fluid is at the expense of a reduction in the internal energy of the fluid. In an adiabatic expansion, the work done W by the fluid is at the expense of a reduction in the internal energy of the fluid. Similarly, in an adiabatic compression process, all the work done on the fluid gas to increase the internal energy of the fluid. So generally, the adiabatic process, the adiabatic expansion or work done W, the fluid is expands to reduction in the internal energy. The fluid is reduction in the internal energy. Similarly, the adiabatic compression process work done on the fluid and increase the internal energy. It will increase the internal energy. For adiabatic process, take place perfect thermal insulation. So generally in adiabatic process take place in the perfect thermal insulation for heat exchangers. We are using this type of insulations, heat exchanger pipes and refrigeration outlet. These are we can use the perfect insulation. There is no heat transfer. So the perfect insulation must be fertilization should be used for installation should be used for the heat exchanger outlets and inlet because there is no heat transfer process on the outside of the system. In the to drive the law, PV power gamma is equal to constant. To obtain the raw relation P and V or reversible adiabatic process, consider a non-flow energy. There is no energy flow in this process, energy transfer in this process, so that non-flow energy. So dq is equal to change in temperature is equal to dV internal energy in terms of du plus dW. So dq is equal to change in temperature is equal to change in internal energy plus change in work done. So for reversible process, dW is equal to P into dV. So first law of thermodynamics, dW is equal to general formula. We have used dq is equal to du plus P into dV. du plus P into dV is equal to 0. Since the adiabatic process, Q is equal to 0 because there is no heat transfer, so Q is equal to 0. For perfect gas, PV is equal to RT is equal to PV is equal to for perfect gas equation. Joule's law, Boyle's law, perfect law, the relation equation PV is equal to RT. PV is equal to P is equal to RT by V. So hence substituting du plus PV is equal to RT, P is equal to RT by U. So here RT by U is used for in the P in the pressure area. So private gas equation. So RT dV divided by V is equal to 0. U is equal to CV into T or du is equal to U is equal to CV into T or du is equal to CV into dt. U is equal to du is equal to CV into dt. CV dt plus RT dV by V is equal to CV into dt plus RT dV by CV into dt plus RT dV by V is equal to 0 because U is equal to, so there is no flow transfer. So temperature is equal to 0. So du plus RTV is equal to 0. Hence we have to consider the U is equal to, so U is equal to CV into T, constant volume at T is equal to constant volume at T or RT dV by V is equal to du cancel, so dd cancel, so U is equal to CV into T, constant volume into temperature, du is equal to CV into dt in terms of T. So CV into dt is plus RT into dV divided by V is equal to 0. CV into T internal dividing both sides by T, we get dividing both sides by T because there is no heat transfer. So the CV into dt by T plus R dV by V is equal to 0. Integrating CV into log E T plus R into log E V is equal to constant. Substituting T is equal to PV by R. Substituting T is equal to PV by R. CV log E is equal to PV by R plus R into log E into V is equal to constant. So in terms of 1 by x is equal to, I have already told 1 by x means integral x is equal integral x is equal to integral x is equal to 1 by x, integral 1 by x is equal to log s. Here also integral dt by t is equal to log e power t and r is equal to log e power into in terms of v is equal to constant. Here substituting t is equal to pv by r, cv into log e is equal to pv by r plus r into log v into u is equal to constant. Dividing throughout the both sides by cv, both sides dividing cv is equal to log e pv by r plus r by cv log E V is equal to constant, log E, V is equal to constant, CV is equal to, again CV is equal to R by gamma minus 1, because CV by CP is equal to gamma, CV by CP is equal to gamma is equal to CP by CP is equal to R is equal to, so that these equation we are using gamma, CP by CV is equal to gamma, so that gamma minus 1 is equal to CV is equal to R by gamma minus 1 is equal to R by CV is equal to gamma minus 1. Hence, substituting the equation log PV by R plus gamma minus 1 log E V is equal to constant, log E PV by R plus log E power V power gamma minus 1 is equal to constant, log E into commonly take log in both outside, PV into V power gamma minus 1 divided by R is equal to constant, log E is equal to PV by gamma divided by R is equal to constant. Here on the PV by R is by gamma, sorry, PV power gamma by R is equal to R E is equal to E power constant is equal to constant, PV by gamma is equal to constant. This is the adiabatic process formula, PV by gamma is equal to constant. The formula only we can use these problem solving areas. Expression of work, reversible adiabatic process for perfect gas. The PV diagram is there. Here are piston gas arrangement. So these systems in the outside the insulated system, gas and piston arrangement. Here temperature P power gamma is equal to constant. Pressure and volume power gamma is equal to constant. The reversible adiabatic process, the work done in the shaded area and the areas evaluated in integration PV power P into dV divided by, therefore P power constant is equal to C. Then again we go to work done is equal to integral V1 V2 C into D power V power gamma. Here we can use C into, we can apply the integration to limits V1 to V2 dV by V power gamma is equal to C. So commonly we can take the C in the outside, V into minus 1, take V into minus gamma plus 1 power 1 into V2 by divided by minus gamma plus 1 divided by V2. So here see commonly take V2 in the outside, it's applying V2 and V1 in the limits. So V2 minus gamma plus 1 minus V1 and minus gamma plus 1 divided by 1 minus gamma is equal to C into V1 power minus gamma plus 1 minus V2 minus gamma plus 1 divided by gamma minus 1. The constant in this equation can be written as P1 V1 power gamma or as P2 V2 power gamma. Hence, the work done is equal to P1 V1 power gamma V1 V1 minus gamma plus 1 minus P2 V2 gamma V2 minus gamma plus 1 is equal to P1 V1 minus P2 V2 divided by gamma minus 1. What done is equal to W is equal to P1 V1 minus P2 V2 divided by gamma minus 1. What done W is equal to R into, so P2 V2 in terms of temperature relations, temperature R is equal to gas constant, temperature relation is final initial temperature minus final temperature, P1 V1 is equal to T1 initial temperature minus final temperature divided by gamma minus 1. Relationship between T temperature volume and temperature pressure. The relationship using the equation gas constant PV is equal to R2, the relationship T and V and T and P may be derived as follows. PV is equal to RT is equal to gas equation, PV is equal to RT, P is equal to RT divided by V. Putting the value of the equation PV power gamma is equal to constant, PV power constant is equal to gamma is equal to constant, RT by V is equal to into P power gamma is equal to constant. So T is equal to T into gamma minus 1 is equal to constant. Also V is equal to RT by P, and substituting in equation PV power gamma is equal to constant. P into RT power P into RT by P, the whole power gamma is equal to constant. T power gamma divided by P into gamma minus 1 is equal to constant. T by gamma minus 1 by gamma is equal to constant. Therefore, for reversible adiabatic process, perfect gas between the states 1 to 2, we can write the states 1 to 2, we can write equation the 4.31 P1 V1 power gamma is equal to P2 in adiabatic process P2 V2 power gamma. Here P2 by V1, P2 by V1 is equal to V1 by V2 power gamma, V1 by V2 power gamma. The equation 4.31 relationship with temperature T1 into V1 power gamma minus 1 is equal to T2 into V2 power gamma minus 1. Here T2 by T1 is equal to V1 by V2 power gamma minus 1. So the equation T1 by gamma minus 1 divided by gamma is equal to T2 by gamma minus 1 by gamma. T2 by T1 is equal to P2 by V1 into gamma minus 1 divided by gamma. The work done is an adiabatic process per kilogram of gas is given by W. The work done per adiabatic process per kilogram of gas work done is equal to internal energy 1 minus final internal energy minus U2. The gain in internal energy perfect gas is given by U2 minus U1 is equal to CV, constant volume at a temperature. Temperature, internal energy is gained in the constant volume process T2 minus T1. What is equal to CV into T1 minus T2. Initial temperature minus final temperature. Also, we know that CV is equal to R by gamma minus 1. Again, substituting, we get V into W is equal to R into T2 minus T1 minus T2 divided by gamma minus 1. Equation PV is equal to R2. So, what is equal to P1 V1 minus P2 V2 divided by gamma minus 1, because R is equal to P1 V1, T2 is equal to T2 minus T1 is equal to constant volume CV T2 minus T1 is equal to constant volume process at outlet is equal to CV into T2 minus T1. Same equation is applied. Same equation is applied in the 4.32. In 4.32, outlet is equal to P1 V1 minus the P2 V2 by gamma minus 1. So another one is polytropic process. In polytropic process, PV power N is equal to constant. In polytropic process, PV power N is equal to constant. It is found that many processes in practice approximate to and reversible law from PV power n. It is found that the process in practice approximate to and reversible law of form PV power n is equal to constant. When n is constant, both vapors and perfect gases obey this type of law closely in many non-flow processes. Such processes are internally reversible. Both vapors and perfect gases obey this type of law. Both vapors and perfect gases obey this type of law closely. Many non-flow processes. So only a flow process and non-flow process. Example: adiabatic process and non-flow process. Such processes are internally reversible. Such processes are internally. The system is internally reversible. We know that any reversible process W work done W is equal to integral PdV, general formula for a process in PV power n is equal to constant. Pressure volume at n is equal to constant. We can P is equal to C by V power n, constant divided by PV power constant. So P is equal to C by constant divided by V power n, where C is equal to constant. C is constant. What and C is equal to V final volume, initial volume minus final volume. So V1 into V2, limit V1 to V2 dV by V power n, dV by change in volume divided by dV by V power n is equal to constant. Is equal to V into integrate V dV, so V power minus n plus 1 divided by minus n plus 1 plus is equal to C into V2 into minus n plus 1 minus V1 minus n plus 1 divided by minus n plus 1 is equal to what is equal to C into V1 power minus n plus 1 minus V2 into minus n plus 1 divided by n minus 1 is equal to P1 V1 power n V1 into minus n plus 1 minus P2 V2 power n V2 minus n plus 1 divided by n minus 1. Since a constant C, we can be written as P1 V1 power n is equal n or as P2 V2 power n. What on W is equal to P1 V1 minus P2 V2 divided by n minus 1. Because polytropic process, what on W is equal to gas constant R into T2, temperature relation T1 minus T2 divided by n minus 1. The work substance undergoing reversible polytropic process, it follows also that for any polytropic process, we can write any polytropic process, we can write P2 by P1 is equal to P1 by V2 power n. The following relations can be derived the following the same procedure as we can done temperature relation T2 by T1 is equal to V1 by V2 power n minus 1. In pressure relation T2 by T1 is equal to P2 by V1 into n minus 1 divided by n. Heat transfer during the polytropic process for perfect gas equation RT is equal to the for non-flow energy equations, the heat flow transfer during the process can found Q is equal to U2 minus U1 plus W. Q is equal to U2 minus U1 plus W. Is equal to CV into T2 minus T1 plus R into T1 minus T2 divided by N minus 1. Q is equal to R into T1 minus T2 divided by N minus 1 minus CV into T1 minus T2. Also, CV is equal to R by gamma minus 1. On substituting Q is equal to R power N minus 1, T1 minus T2 minus R power R divided by gamma minus 1 into T1 minus T2. Q is equal to R into T1 minus T2. Q is equal to R into T1 minus T2 into 1 by N minus 1 minus 1 by gamma minus 1. Is equal to R into T2 minus T1, T1 minus T2, R into T1 minus T2, gamma minus 1 minus N plus 1 divided by gamma minus 1 into N minus 1 is equal to R into T2 minus T1 into gamma minus N divided by gamma minus 1 into N minus 1. So we used is and substituting the equation in the CV is equal to constant volume is equal to R by gamma minus 1. This is the fundamental equation. Here the heat transfer Q is equal to R by universal gas constant R, gas constant R divided by N minus 1 index N minus 1 into temperature T1 minus initial temperature minus final temperature minus R by gamma minus 1 into initial temperature minus final temperature. So these equations we can use, we can write W is equal to R into T2 minus T1 divided by N minus 1. What time is equal to? In a polytropic process, the index N depends only on the heat and work quantities during the process. The various process consider the in the polytropic process, the index N is depend on by one only on the heat and work quantities during the process. In the adiabatic process, the PV power N is equal to PV power N is equal to nearly 1.2, so unity. So less than 1 or unity. So here the various processes considered earlier as the special cases polytropic process for perfect gas. For example, N is equal to 0, P was equal to P is equal to constant. N is equal to infinity, P is equal to power infinity is equal to constant. P 1 by infinity by is equal to constant. So P when N is equal to 1, P V is equal to constant, T is equal to constant. Pressure volume constant, temperature constant. Since PV by D is equal to constant for perfect gas, when N is equal to gamma, PV power gamma is equal to constant or reversible adiabatic process. So or reversible adiabatic process. State 1 to state A is constant pressure cooling, N is equal to 0. State 1 to in constant pressure cooling process, N is equal to 0. State 1 to state B, isothermal compression, N is equal to 1. Isothermal means there is no heat change. So the temperature are constant. In constant isothermal constant compression, N is equal to 1. State 1 to reversible adiabatic process, N is equal to in reversible adiabatic process, N is equal to gamma. So 1 to 2 state D constant volume process, N is equal to infinity. Similarly, state 1 to state A is constant pressure heating, N is equal to 0. State 1 to state B, yes, sorry, B dash is isothermal expansion, N is equal to 1. State 1 to state C, the reversible adiabatic expansion, N is equal to gamma. So, in state 1 and state 2, constant volume cooling, N is equal to infinity. So, it may be noted that since the in the figure shows the constant pressure and volume diagram because the N is equal to 0 in the constant volume process, in the constant N is equal to 0, N is equal to 1, state 1 to 2, 1 to 2 in the A dash, state 1 of state A dash, in A dash N is equal to 0 because constant pressure is equal to constant, so that N dash N is equal to 0. The figure indicates the same brackets. So another topic is perfect gas equation, pre-expansions. Consider two vessels 1 and 2 interconnected by a short pipe. So 1 and 2 the interconnected by the short short pipe interconnected by the short pipe. 1 minute. Consider two vessels, one and two, interconnected by a short pipe with a valve. So two vessels which are interconnected a short pipe with a valve, a perfectly thermally insulated. The pipes are perfectly thermally insulated. Initially, let the vessel one be filled with a fluid. The vessel one is filled with fluid at a certain pressure, and let two be completely evacuated. So completely one is filled with the certain pressure, and two is completely evacuated means there is a no fluid inside the vessel. When the value when the value A is open to the fluid in one, with the expand rapidly to fill both vessel 1 and vessel 2. So first vessel is filled with fluid, second vessel is in empty. First the vacuum is the fluid will be opened, and what will happen? The fluid 1 will be expand rapidly and to fill both vessels. So the fluid fill both the vessel 1 and 2. The pressure finally will be lower than the initial pressure. The pressure finally lower than initial pressure in vessel 1. This is known as free air and unrestricted expansion. This is known as free or unrestricted expansion. The process is highly irreversible. The process is highly irreversible since the fluid is eddying continuously. Since the fluid is eddying continuously during the process. Now applying first law of thermodynamics or non-flow process. First law of thermodynamics or non-flow process equation between initial and final stage. Q is equal to U2 final internal energy minus internal energy plus work done. In this process, no work is done on or by the fluid. In this process, no work is done. No work is done on or by the fluid, since the boundary of the system does not move. The boundary of the system does not move. No heat flows or from the fluid since the system is well dacked. So no heat flow, no heat transfer is heat flow is because the system is well dacked. The process is therefore adiabatic or reversible. The process is adiabatic because there is no heat transfer or there is but irreversible. The process therefore adiabatic, no heat transfer, and the process is irreversible. So U2 minus U1 is equal to 0. Then U2 is equal to U2 is equal to U1. In the free expansion, therefore, the internal energy initially equals the internal energy finally. In free expansion, therefore, the internal energy initially equal the internal energy finally. So the internal energy, initial internal energy is equal to final internal energy. So perfect gas U is equal to CV power CV into T. So here the figure shows vessel 1 and vessel 2. The valve is connected. First, initially the valve is closed. The fluid in the vessel 1, the fluid is in a vessel 1 in fluid. The vessel 2 is empty. So when open the valve, the fluid goes to vessel 1 to vessel 2. The pressure is dropped. So what will happen? Reversible adiabative will be formed. The free expansion, the perfect gas CV, constant volume CV into T1, temperature 1 is equal to CV into T2. Initial temperature is equal to final temperature. So T1 is equal to T2. That is for perfect gas equals outgoing for free expansion. The internal temperature is equal to final temperature. Here a chart or some formulas are there. Process and perfect gas or a unit mass. Some formula is there. First one is the process. So different type of process: the constant pressure process, constant volume, constant temperature, reversible adiabatic, or polytropic. Second one is heat added. Third one is integral. Integral is with respect to pressure in terms of change in volume. Third one is PVT relations. And finally, specific heat. So specific heat or C. So first constant pressure process, the index N is equal to 0. Was already explained. Heat added. Constant pressure process Cp is equal to constant pressure Cp is equal to T2. Final temperature minus initial temperature. Integral P into pressure in terms of pressure is equal to constant pressure. Pressure is equal to constant, and volume is equal to initial to final volume. So that V2 minus V1. PVT relation temperature T2 in terms of T2 final temperature divided by T1 is equal to final volume divided by V1 initial volume. Specific heat C is equal to Cp. So that Cp specific heat. Constant volume process N is equal to infinity. Cv is equal to volume is constant. So constant specific volume Cv into Tt final temperature minus initial temperature. But volume is constant. So in perfect gas volume constant. The C is equal to internal PdV volume constant, so that there is no heat and so no work done. So C is equal to 0. And T1 temperature relation T2 by T1 initial temperature divided by final temperature. Temperature will be constant volume pressure. Temperature increases, so T2 by T1 is equal to P2. Pressure volume is constant, so that P1 pressure is equal to P1 divided by P2 Cv. Cv is equal to specific volume. Constant temperature. In constant temperature is equal to N is equal to index. N is equal to 1. P1 V1 log E power V2. P1 V1 pressure 1. Volume 1 is equal to log E power V2. Final volume divided by initial volume. P1 V1 is equal to PV relation initial volume. Pressure at 1 and volume at 1 is equal to pressure at 2 and volume at 2 is equal to is infinity. Reversible adiabatic process N is equal to gamma. Pressure adiabatic process N is equal to infinite gamma. N is equal to gamma. Heat added 0. So reversible adiabatic process, the heat added means there is no heat adding in the system. So heat added, no heat transfer. So that heat added is equal to 0. In the integral 1 to 2 PdV, P1 V1 minus P2 V2 divided by gamma minus 1. It's a formula, Watton formula. And another one is PVT relation. P1 V1 power gamma is equal to P2 V2 power gamma. Here gamma is used divided by gamma. T2 by T1 is equal to V1 by V2 power gamma minus 1. P2 by V1 into gamma minus 1 divided by gamma. So in specific heat is equal to 0. In polytropic process, N is equal to N. Cn is equal to T2 minus final temperature minus initial temperature Cv into gamma minus N divided by 1 minus N into T2 final temperature minus initial temperature divided by Watton, gamma minus n divided by gamma minus 1 into Watton. So it is non-flow process. So Watton is not a Watton is done on this system. Integral 1 to 2 PdV P1 V1 minus P2 V2 divided by n minus 1. P1 V1 power n is equal to P2 V2 power n. T2 by T1 is equal to V1 by V2 power n minus 1. So it's equal to P2 by P1 power n minus 1 divided by n1. So small fundamentals formula, some problems are there. Just I can explain the fundamental problems. Today I can explain some fundamental problems. Next class we can go some exact problems. So first problem, in an internal combustion engine. So an internal combustion engine, IC engine, ordinary engine means during the compression stroke. So the engine has 4-stroke: suction, power, compression, and exhaust stroke. The compression. So compression stroke, the heat is rejected. The compression stroke heat is rejected. For ever in the to the cooling water is 50 kilojoule per kilogram. In the heat is rejected to the cooling water. Heat is rejected to the cooling water 50 kilogram per kilojoule per kilogram, and work input is 100 kilojoule per kilogram. The system work input to the system is 100 kilojoule per kilogram. Calculate the change in internal energy of the working fluid starting whether it is a gain or loss. Whether it is the energy is internal energy is gained or internal energy is lost. We have to calculate the whether the internal energy is gaining or so the here heat rejected to the cooling water Q is equal to minus 50 kilojoule per kilogram. Heat rejected because heat is rejected because the system is the work is on the system. The work is done. Work done is on the system. So that the Q is equal to minus 50 kilojoule per kilogram. Minus n is since the heat is rejected and the system. So heat is rejected also, so that minus n is used. Work input W is equal to input of the system. So my work is supplied to the system. So here also we can use minus 100 because the work is on the system. Work is done the system positive. Work is on the system negative. So minus negative minus sign work is supplied to the system. So that W is equal to minus 100 kilojoule per kilogram. Using the relation Q is equal to U2 minus U1 plus work done W. So Q is equal to minus 50 kilojoule per kilogram. Q is equal to heat transfer is equal to U2 minus U1 minus 100. So U2 minus U1 is equal to minus 50 plus 100. Minus 50 plus 100 is equal to 50 kilojoule per kilogram. Hence, gain in internal energy 50 kilojoule per kilogram. So it is a simple problem. And second one is, in a motor cylinder, the compressed air gas and internal energy. In a motor cylinder, the compressed air gas and internal energy of 450 kilojoule per kilogram at the beginning of the expansion. In the motor cycle, the compressed air, motor cycle, compressed air has an internal energy of 450 kilojoule per kilogram. At the beginning of the expansions, at the beginning of the expansion and an internal energy of 220 kilojoule per kilogram. After expansions, if the work done by the air during the expansion is 120 kilojoule per kilogram, calculate the heat flow and the heat flow and from the cylinder. An air motor cylinder, the compressed air has an internal energy of 450 kilojoule per kilogram. At the beginning of the expansion, the internal energy in the beginning of the expansion, the internal energy is of 220 kilojoule of kilogram. After expansion, so after expansion, if the work done on the air, the expansion is to 120 kilojoule per kilogram. The work done is done on the 120 kilojoule. Calculate the heat flow and from the cylinder. So internal energy beginning of the expansion. So internal energy U1 is equal to internal energy. The notation is U1 data. So 450 kilojoule per kilogram. Internal energy after the expansion. So yeah, first internal energy is beginning internal energy is notation is U1. Final internal energy is U2. I was already explained in the formulas in the previous classes. So work done by the air during the expansion W is equal to 120 kilojoule per kilogram. Heat flow work done by the air. So work done by the air is equal to during the expansion W is equal to 120 kilojoule. Heat flow Q is equal to using the relation Q is equal to general formula Q is equal to U2. So internal energy finally expansion internal energy at the expansion U2 minus U1 plus W. Q is equal to U2 220 kilojoule per kilogram 220 plus minus final internal energy at beginning is equal to 450 plus work done is equal to 120. So minus 230 plus 120 is equal to minus 120 kilojoule per kilogram. So hence minus sign indicates the heat is rejected by the air. So that the minus sign is indicates. So another problem 0.3. These are fundamental problems. 0.3 kilogram of nitrogen gas as 100 kilopascal and 40 degrees centigrade is contained in a cylinder. The piston is moved compressing nitrogen until the pressure becomes 1 megapascal. 0.3 kilogram of nitrogen gas at 100 kilopascal. 0.3 for nitrogen gas at 100 kilopascal at 440 degree centigrade. Temperature is 40 degree centigrade is contained in a cylinder. Or cylinder, okay, it's containing cylinder. The piston is moved. Piston on the move compressing and nitrogen until the pressure becomes 1 megapascal. The piston moves until the pressure becomes 1 megapascal. So this indicates the pressure is at a constant 1 megapascal. So the constant pressure process I can just as that and the temperature becomes 160 degrees centigrade. The work done during the process is 30 kilojoule. The temperature becomes 160 160 temperature, and the work done during the process and the work done during the process is the 1 megapascal. The temperature becomes 160 degrees. The work done during the process is 30 kilojoule. Calculate the heat transfer from the nitrogen to the surroundings. Calculate the heat transfer. CV for nitrogen is equal to 0.75 kilojoule per kilogram Kelvin. CV power for nitrogen, constant volume for nitrogen is 0.75 kilojoule per kilogram Kelvin. Mass of nitrogen M is equal to 0.3 kilogram. Mass of nitrogen. So in the piston cylinder, the figure shows the piston cylinder arrangement, cylinder, and inside the nitrogen gas is there. These are boundary and piston movements. So what ton is equal to the CV is equal to constant volume. So the temperature before compression is equal to 40 degree temperature. 40 plus 273 added the 3 Kelvin. Convert Kelvin. The because SI units we can you follow the Kelvin. So 313 and temperature after compression 160 plus 273 is equal to 433 Kelvin. The work done during the compression process W is equal to minus 30 kilojoule. According to the first law of thermodynamics, Q is equal to delta U plus W is equal to delta U plus W is equal to U2. Final U2 minus U1 plus W. MCB constant volume into mass into constant volume T2 minus T1. So final temperature minus internal temperature plus work done is equal to MCB mass into constant volume. Mass is equal to Q1. Mass is given 0.3 into constant volume process 0.7 is also given in given data. Final temperature 433 minus 313 minus what is equal to minus 30. So minus 30 because the what is during the compression process what on the system, so that we can take the minus 30 is equal to minus 3 kilojoule. So the heat is rejected during the process. So the answer says that the heat is rejected on the system. So the note when work has been taken in past negative work has been taken negative because it has been supplied from outside. It has been the work is supplied when, so that I was told the work has been supplied from outside. Another formula, another problem. When a stationary mass of gas was compressed without friction, when a stationary mass of gas was compressed without friction at constant pressure, its initial state of 0.4 meter cubed and 0.105 megapascal was found to change to final state of 0.20 meter cubed and 0.105 megapascal. There was a transfer of 42.5 kilojoule of heat from the gas during the process. How much did the internal energy of the gas change? How much the internal energy of the gas change? When the stationary mass of gas was compressed, when gas is compressed without friction, no friction, at a constant pressure, the process is constant pressure, initial state 0.4 meter cubed, and state means initial volume is 0.4 meter cubed and 0.105 megapascal. Pressure is equal to 0.105 megapascal, that is initial pressure found. Change the final state. Final volume is 0.20 meter cubed and 0.105 megapascal. So final pressure is 0.105 megapascal. There was a heat transfer, 42.5 kilojoule of heat. The gas during the process, how much did the internal energy of the gas change? So here the piston and cylinder arrangement, inside the gas is there. The Q is equal to 42.5 kilojoule in piston and weight is in the upward position, the boundary. So a pressure gas P1 is equal to 0.105 megapascal, volume 0.4 meter cubed, and final state pressure is equal to 0.105 megapascal, volume is equal to 0.20 meter cubed. Pressure used constant pressure, heat transfer Q is equal to minus 42.5 kilojoule. Minus n indicates the heat rejected. Change in internal energy delta U is equal to U2 final temperature minus internal temperature. First law of stationary system in a process gives Q is equal to delta U plus W. Q is equal to delta U plus W general formula. So Q1 to 2 is equal to U2 minus U1 plus W1 to 2. So work done 1 to 2. So internal formula work done 1 to 2 is equal to volume, initial volume, integral initial V1 to V2. Integral PdV is equal to P into pressure into volume, final volume minus initial volume, because in the constant volume process, so that we can use, because there is in the problem also indicates compress without pressure at constant pressure, compound without pressure at constant pressure, so that we can use the P into V2 minus V1. So we can apply this P pressure also given, V2 minus V1 also given, megajoule minus 21 kilojoule. Megajoule is equal to minus 21 kilojoule. So 1 megajoule is equal to 10 power 3 kilojoule. 1 megajoule joule is equal to 10 power 3 kilojoule. Here substituting the value 1 to 2 equation, we get equation is equal to which equation? This Q is equal to delta U plus W. This equation we can apply. So internal energy 42 minus 42.5 is equal to U2 minus U1 minus 21. So U2 minus U1 is equal to minus 42.5 plus 21 is equal to minus 21 by and 5 kilojoule. 5 kilojoule. Hence, the decrease in internal energy is equal to 21.5 kilojoules. So a container is divided into another problem, very important. These decrease in internal energy, these are fundamental problems only. A container is divided into compartments by a partitions. The container is completely insulated, so that there is no heat transfer. The container is completely insulated, so that there is no heat transfer. One portion contains gas at the temperature T1 and pressure P1, while the other portion also has the same gas, but at the temperature T2 and pressure P2. How will the first law of thermodynamics conclude the result if partition is removed? So the container divided into the two compartments by a partition. One partition is there in the container. The container is completely insulated. The container is there, so container is completely insulated means so adiabatic process. There is no heat transfer. So there is no heat transfer. So this process in adiabatic process, one portion contains gas. One portion contains gas at a temperature T1. Temperature is in T1 and pressure is P1. Pressure is in P1. While the other portion also gas the same gas. So other portion gas also in the same gas. But the temperature T2 and temperature T2 and pressure P2. How will be the first law of thermodynamics conclude the results if the partition is removed? The partition is removed, the pressure and temperature will be interchanged. So the first law of thermodynamics, what they told, del Q means change in temperature is equal to change in internal energy plus change in work done. So del Q is equal to del U plus del W, where the partition is removed, change in internal, change in temperature. So change in temperature. So here the temperature is constant. T2, T1, change in temperature. Del Q is equal to 0. Del W work done is equal to 0. Del U internal energy is also 0, because the partition is removed, the gases one, the portion one and portions two also interchange, and the gas goes one portion to another portion. The conclusion is there is the conversion of internal energy. Conclusion is the internal energy is changes from one form to another, one side to another vessels, one vessel to another. So another problem, air enters a compressor 10 sorry, air enters a compressor at 10 power 5 Pascal and 25 degrees centigrade, having volume of 1.8 meter cube per kilogram, and is compressed to 5 into 10 power 5 Pascal isothermally. Determine work done, change in internal energy, and heat transfer. Internal pressure of air P1 is equal to 10 power 5 Pascal. Internal temperature at air T1 is equal to 25 plus 273 is equal to 298. The air enters the compressor. The compressor air pressure is equal to 10 power 5 Pascal and temperature is equal to 25 degree. Volume is equal to 1.8 meter cube per kilogram and compressed. So initial volume is compressed. The pressure, the air is compressed. Initial to final 5 into 10 power 5 Pascal in isothermally. In isothermally, the temperature is constant, because in isothermal process the temperature is constant. Determine work done, find out the work done. First we have to find out the work done, second change in internal energy, and finally we can find out the heat transfer. Okay, solution. Internal pressure of air is equal to P1 is equal to 10 power 5 Pascal. Internal temperature of air is equal to T1 is equal to 25 degree plus. We have to convert that degree into Kelvin. So 25 plus 273 is equal to 298 Kelvin. Final pressure of air P2 is equal to 5 into 10 power 5 Pascal. Final temperature of air is equal to T2 is equal to T1 is equal to 298 Kelvin. So isothermal process. Because in isothermal process, so that there is no initial temperature is also same and final temperature is also same, so that the T2 is equal to T1. Since it is close to steady state condition, we can write the first law of thermodynamics. Q is equal to U2 minus U1 plus W per kilogram is the formula. Isothermal process, the W1 to 2 integral 1 to 2, 1 to 2 PdV is equal to P1 V1 log E power P2 by P1. Because isothermal process, the formula is there. The P1 V1 is equal to P2 V2 for isothermal process. W1 to 2 is equal to P1 V2 minus 5, 1 to 2 is equal to minus P1 V1 is equal to P2 V2 is equal to minus 10 power 5 into 1 power 1.8. This formula can P1 V1 is equal to minus 10 power 5 into 1.8 log E power 1.8 into log E power 1 into 10 power 5 pressure P1 1 into 10 power 5 divided by 5 into 10 power 5 is equal to substitute. The answer is minus 289.7 kilojoule per kilogram. Minus sign indicates that the work is supplied to the air. Minus sign indicates work is supplied to the air. Work done on the air is equal to 289.7 kilojoule per kilogram. Since the temperature is constant, the internal energy U2 minus U1 is equal to 0. Change in internal energy is equal to also 0. Again, Q1 to 2 U1 U2 minus U1 plus W. U2 minus U1 is equal to internal energy is 0. So it's equal to 0 plus minus 289.7 is equal to minus 289.7 kilojoule. Minus sign indicates that heat lost from the system to the surrounding. Minus sign indicates heat lost from the system. Okay. Another one problem. It's a very simple fundamental problem. A cylinder containing the air, cylinder containing the air compresses the system. Cycle is completed as follows. Number one, 80,000 Newton meter of work is done by the piston on the air during compression stroke, and 45 kilojoule of heat are rejected in the surroundings. During expansion stroke, during expansion stroke, 1 lakh Newton meter of work is done by the air and the system and the piston. Calculate the quality of heat added to the system. So heat added to the system. Here you can see the volume, volume process. The pressure is equal to 2 to 1. Pressure is dropped into 2 to 1. Volume is V. Volume is 1 to 2. Volume is increase. Pressure is decrease. Here 2 to 1. Here the process, a cylinder containing air compresses the system cycle completed is 82,000 Newton meter. Work is done by the piston. The piston is done under 82,000 Newton meter during the compression stroke. In the compression stroke, 45 kilojoule of heat are rejected. So heat is rejected. So that the 45 is minus 45 because the heat is rejected during the expansion stroke. 1 lakh Newton meter work is done. In the expansion stroke, 1 lakh Newton meter is done piston. Calculate the quantity of heat added to the system. Quantity of heat added to the system. Work done by the system is of air is equal to 1 to 2. Work done by the system 1 to 2 is equal to 82,000 Newton meter, because work is done by the system. Work is done by the piston. So in kilojoule minus 82 kilojoules. So heat rejected by the system 1 to 2 minus 45, because 1 to 2 is minus 45. Heat is rejected. Okay, Q1 to 2 is equal to U2, internal energy, final energy minus initial internal energy is plus work done is equal to general formula. So these are given. Temperatures are work done as given minus 45. Heat is rejected because we can use minus 45 is equal to U2 minus U1 into plus work done is equal to also minus 82, because the system is work done by the system, so that we can use minus 82. U2 minus U1 is equal to 37 kilojoule. Um, work done by air on the piston is equal to work done by air on the piston is equal to W1 to 2 to 1 is equal to 1 lakh Newton meter. So it's equal to 100 kilojoule. We can write in 100 kilojoule. 1 kilojoule is equal to, so now Q221 is equal to internal energy. The same formula I can use internal energy, initial internal energy minus final internal energy plus work done. So minus 37 plus 100 kilojoules equal to 63 kilojoules. So quantity of heat is added in the system 62, 63 kilojoule. Here, um, calculate the quantity of heat added on the system. The question is calculate the heat added on the system. Okay, today class over. Next class we will meet the next class. Okay, thank you.